Chapter 7 is the last chapter that we cover in this class. And we cover something called integrals, and in the first section we're going to cover something called antiderivatives. Really what we're doing in this last chapter is that everything we've done so far has been taking derivatives. Now we're going to actually look at how you can work backwards. So let's say you have the derivative, for example, and you want to get back to the original function. That's the main idea of what we're going to look at in Chapter 7. Okay, so first this idea of the antiderivative. If you look here, what you have, if you look at a function 7x, if you take the derivative, the answer is 7. But now we're going to say to get the antiderivative is to go from 7 and then come up with the 7x. And when we actually do look at the rules for integrals and antiderivatives, you're going to see that we're doing the reverse of what you would do to take the derivative. And if we keep going, same idea for the rest of them. The derivative of x squared is 2x. So that means the antiderivative of 2x is x squared. The derivative of x cubed is 3x squared. So the antiderivative of that is x cubed. Okay, so for this first one, before we look at any of the rules, let's just think about working backwards. So if we have, think about it as like if our derivative is 20, what was the original function? And that would be 20x. And so at this point, because we're much more comfortable, because we've been taking derivatives for so long, since we're more comfortable with derivatives, it's always good to check your work. So if the answer is 20x, just check it. Okay, so the derivative of that is 20. So that means we should have the correct antiderivative. Let's look at the next one. We want to think about what would create a derivative of x cubed. Well, we know when we take the derivative, your exponent goes down by 1. So that means it would need to be x to the 4th. And now if we check it, if you take the derivative of x to the 4th, that's 4x cubed, which means we found our answer. Okay, let's look at the next one, 9 plus 2x. Well, to get to the derivative of 9, we would need to start with 9x. If we think about the 2x, the same thing is that since that's x to the 1, we need to go up to x to the 2. And now let's go ahead and check the derivative. The derivative of 9x is 9, so that one checks out, and the derivative of x squared is 2x. So that checks out too. If we just have an x, well, what I was saying before is that since this is x to the 1, we know that our antiderivative needs to be x squared. But the thing is that when we take the derivative here, the answer is 2x. So we're close, but we're not quite there yet. But what I could do is I could actually put a 1/2 in front, and that would allow this 2 to sort of cancel out. So now if we check it, the derivative of 1/2 x squared, well, the derivative would be 1/2 times 2x, and then the 2's cancel, leaving just an x. So now it checks out. So we found the antiderivative. Looking at x cubed, I'm going to write down, looking at x squared, I'm thinking ahead here, it's going to be x cubed, but same thing as if we take the derivative of x cubed, that's going to be 3x squared. But we're looking for just x squared without the 3 there. So we can actually multiply x cubed by 1/3. That way when we take the derivative, we would get 1/3 times 3x squared, and now the 3's cancel, which means it checks out. The derivative of 1/3 x cubed is x squared. So that means the antiderivative of x squared is 1/3 x cubed. Okay, for e to the x, well, since the derivative of e to the x is e to the x, that means the antiderivative of e to the x is e to the x. 1/x, the answer for this one is actually going to be ln of x, and that's because the rule here is that the derivative of ln of x is 1/x. What if our function is 0? Well, we know that when you take the derivative of a number, the answer is 0. So really, the answer here could be any number. For example, we could have that if it were 5, the derivative would be 0. If it were 10, the derivative would be 0, and so on. So it doesn't matter, but any number here, the derivative would end up being 0. So the antiderivative for 0 could be any number, any constant. And that kind of leads into this next thing that we're going to look at here. Okay, so first, thinking back to derivatives again, not antiderivatives. What I actually want us to do here, we have 3 functions. I want us to take the derivative for each one. So if we have x cubed, the derivative here is 3x squared. If we have the function x cubed plus 3, the derivative would be 3x squared plus 0, which is just 3x squared. If we have the function x cubed minus 1, the derivative, 3x squared minus 0, which is just 3x squared. So what's happening here is that our original functions were different. They're very closely related, but they're not the exact same. But the derivatives ended up being the exact same. And so now if we think about the antiderivative, remember that's moving back to that original function. The question is, if we had started with 3x squared and we're trying to find the antiderivative, how do we know if the answer should be x cubed, or x cubed plus 5, or x cubed minus 1, or x cubed plus or minus any constant? We don't really know. There's like this bit of confusion there, which is basically what we need to keep in mind when we take the antiderivative, is that there could have been a constant there that went to 0, and so we don't quite know what that was. And then we use this notation of a c for something like that. So here now we're starting to get into this integral notation. So the integral notation is this little kind of S-looking shape, but a little bit longer. So that means the integral here. And the dx here is indicating the variable. So the variable that we're taking the derivative of here is with x. It also kind of follows from that idea of differentials. And so if we're trying to get back to that, let's say, original y, original function, you could think about it as the fact that y is equal to the integral of this. So that's why I mentioned in that section of differentials that we're kind of splitting up that dy and dx, and it leads into what we were going to look at in the next chapter, which is pretty much right now. And so this is kind of where the notation comes from. There's not really much we need to do here, but you do need to know that there's going to be this dx sort of tacked on to the end of our function. But the part that we're trying to find that antiderivative or integral for is going to be listed right before it. So that's kind of the main part to focus on. Okay, so that's a little bit about notation. But again, from what we did on that previous page, the idea is once you take the antiderivative, you actually add a c there. And the c is just standing for any constant, because we just talked about how here are three functions that have the same derivative. And so now if we're trying to find the antiderivative going backwards, how do we know what constant it was? That's why we put the plus c there. So the answer here, so this means integral or antiderivative. So we're working backwards, and we've already talked about how that would be. X cubed. But again, we weren't sure what the constant could be, so we just put the plus c there to indicate that it could be some constant. And then if we think about going backwards, we would take the derivative. So the derivative of x cubed is 3x squared. So that checks out. And then the derivative of any number that I would put here would be 0. And so that's why there's nothing else there, just the 3x squared. Now let's look at the rules for integration. So here's the rules that we're going to look at for integrals. What I really want you to notice is that idea of doing the reverse thing as what we had done when we were taking the derivatives. And so just to notice some patterns here, if we have a constant, now that becomes constant times x, because to take the derivative, if we had, and I guess I shouldn't call it a constant, but a coefficient, but when we took the derivative of something like 5x, then the answer would just be 5. So this is really the reverse of that rule. And same thing for the power rule. If we have something with an exponent of n, now we're increasing that exponent. So we're adding to the exponent instead of subtracting. And we're dividing by that number instead of multiplying. But with all of these rules, because we've done so much more with derivatives at this point, I think the best strategy is to, once you've gone ahead and integrated, to just check it by taking the derivative to see if you get back to where you had started. So let's look at some examples. So the integral of 7 is going to be 7x, because if we check it, the derivative of 7x is 7, and then we add in the plus c. And that's our final answer. Again, just to emphasize some of the notation, what we're focusing on is the function here. And at this point, we're not really doing much with the dx. We can just look at that as just telling us the variables that we're working with for this function is x. For x to the fifth, if we want to integrate it, I'm going to go ahead and instead of just thinking about going backwards, I'm actually going to go ahead and just try and specifically apply this power rule to show you what it looks like when we apply the power rule for integration. So in this case, we would say that the exponent is 5, so n is equal to 5. So applying that rule, it would be x to the 5 plus 1 over 5 plus 1. And then that's it. That would be our answer. We would just simplify it. But then before I do that, I want to make sure that I don't forget to just add the c in there. And then simplifying that, that becomes x to the 6th over 6. You could write it like this, or you could write it as 1/6 x to the 6th. Either one would be correct here. Okay, here's an example where we have a function with kind of 3 different terms here. So the idea, and again, I'll go back to the rules here. The sum and difference rule is basically just trying to say is if you have separate terms, so they're separated by addition and subtraction, you can just integrate them separately. And this was really the same thing we did for derivatives as well, is that you could differentiate them separately as well. So here we're going to just look at each one separately. And just note we do have a variable change here. So you see how there's the t here, so then at the end, instead of it being a dx, now it's a dt, just indicating the variable that we're working with here. All right, so let's look at the first one. So we want to integrate that. So I'm going to write it as 6 times. We're going to use the power rule here for integration, where n is equal to 2. So that becomes t to the 2 plus 1 over 2 plus 1. And now I'm going to move on to the next one. 8t. So it's going to be minus 8. And then t, you could use the power rule as well for integration. In this case, n is equal to 1. So that becomes t to the 1 plus 1 over 1 plus 1. And then now let's look at the last one, 7. So that would be plus 7t. And then the very last step is to add in the c. Well, I guess I shouldn't say very last step because we do still need to simplify here. So let me go ahead and rewrite this. 6, and this will be, this ends up being 1/3 t cubed minus 8, and then 1 over 2 t squared plus 7t plus c. So I can simplify a little bit more for each one. Like I could simplify the 6 divided by 3, 8 divided by 2. So we get 2t cubed minus 4t squared plus 7t plus c. And this is our final answer. Okay, what I do want to go over for this one was I had mentioned, how do you check your work? And you can check it by just taking the derivative. So let's go ahead and try that. So if I take the derivative of this, I get 2 times 3t squared minus 4 times 2t plus 7 plus 0, which is equal to 6t squared minus 8t plus 7. And so if I check what we originally had inside our integral, that's the exact same thing. So that would be kind of checking your work. And at that point, we'd say, okay, we feel pretty confident with our answer now because we've gone ahead and checked it. Now let's look at another function. So we have an e function here. If it were just, let's say, the integral of e to the x, that answer would just be e to the x. This one has a little bit more to it because the exponent is more than just an x. So just like when we would take the derivative of an e with something more in the exponent besides just the variable x, then we had to use the exponential function derivative rule. Let's go ahead and look at the rule for this, the exponential function rule for integration. So if we look here, we do have e to the kx, but then we divide by the value of k. So that's the extra step here versus just the exponential rule. So the only difference is when you have more in the exponent. So to take the integral here, the 3, I'm just going to leave it in the front, so it's 3 times, and now take the integral of e to the negative 0.2x. So that's going to be e to the negative 0.2x divided by negative 0.2. That's just applying the exponential function rule for integration. There's nothing else in there, so then the last step here would be plus c, and then now let's simplify. So here, if you wanted to, you could plug into your calculator like 3 divided by 0.2, and that's going to give you 15. And it's going to be a negative 15 because that was negative 0.2. So it's negative 15 e to the negative 0.2x plus c, and that's the final answer. That's our integral. For this one, let's go ahead and try and check our work also. So check our work by taking the derivative. So to take the derivative here, I would leave the negative 15 in the front, times, and the derivative rule here is that we will have e to the negative 0.2x. But then we also have to multiply by the derivative of that exponent. So the derivative of negative 0.2x is negative 0.2. And if we plug that into the calculator, 15 times 0.2 is 3. And it's going to be positive since we have a negative times a negative. So we end up with 3e to the negative 0.2x, which was exactly the function that we had started off with. So that lets us know that our integral is correct. So with a function like this, we're dealing with the variable p, but the process is the same. You might be tempted to use the power rule for something like this. So let's say if you tried to apply the power rule, you would end up with p to the negative 1 plus 1 over negative 1 plus 1, which is p to the 0 over 0, which is undefined because we can't divide by 0. So why is this not working? What's happening here? Let's go back and look at the rules. The reason this one doesn't work is because the integral that we're actually looking for is log. We're going to use the natural log for this one. And so because I had specifically written that one with negative 1, because we get so used to thinking we see an exponent, so go ahead and apply the power rule. So if that happens, let's say if you forget and you accidentally apply the power rule, just know that you're going to get divided by 0, which means, wait, that's weird, what's going on? Hopefully it triggers, like, in your mind, okay, what's happening? Oh, that's right, that's because specifically if the exponent is negative 1, that actually is the natural log rule. So that's the only time where the exponent, we would not use the power rule, and instead we'd use this natural log integration rule instead. And if it helps for this one, I could rewrite it even as 4 times 1 over p dp, which maybe this one looks more like, oh yeah, that's right, I need to use the log rule instead. So the integral here is going to be 4 times ln of p plus c. All right, so for these problems, why is there this absolute value? The absolute value is there because at this point we don't really know what p is. P is a variable. The whole point of putting that there is basically just to indicate that if we are to take the natural log, the argument, which is really that part highlighted in green, must be positive. And that's because taking the log, a regular log, any log, or the natural log would be undefined if you tried to plug in a negative value. So if you tried even in your calculator to plug in something like ln of negative 1 or ln of negative 5 or something like that, you're going to get an error. So that's why in that rules, in the rules listed, there is that absolute value there. It has to do with this. Okay, so that is our integral. We could still check our work. And when you check it, you could just kind of view it as 4 ln of p like this instead. And so if you take the derivative, you get 4 times the derivative of ln of p would be 1 over p. The plus c is 0, so that gets us right back to 4p, which is the same thing as 4p to the negative 1. Okay, so for now, like a problem like this, it does look more complicated than what we've seen already, but we can simplify this. But what you want to really be careful of is that you don't want to try to just take the derivative of this, take the derivative of this, take the derivative of this all separately. The reason that doesn't work in this case is because there is this division here. So you've got this numerator divided by this denominator. If we were taking a derivative, that's when we would actually use a quotient rule. There's actually no quotient rule or no product rule for integration, so that's not going to work here. But what we could do is try and simplify first, and then we can take the derivative. So we could simplify this because when we do have a fraction and there's only a single term in the denominator, that means that we could split it up. So we could split it up and say this is the same thing as cube root of x over x squared minus 7 over x squared. So how does that help us? Well, I could now rewrite these and I could actually simplify that first one so that it's in the form where we're going to be able to just go ahead and use the power rule for integration. So let me go ahead and simplify this first fraction to start. So x cubed is the same thing as x to the 1/3. So a rule for exponents is that if you have a division like x to the something over x to the something, you can actually go ahead and subtract the exponents. So this is nothing to do with differentiation. This is only an exponent rule from algebra. So if I try to combine them, I could multiply the 2 by 3 over 3, so that's 1/3, minus 6 over 3, so we get x to the negative 5/3. So I simplified cube root of x over x squared to x to the negative 5/3. And yeah, the exponent's a fraction, but we could still use the power rule even if it's a fraction. And we could also try and simplify the second fraction. We don't have to do as much here, but we could say that when we have an exponent in the denominator, we can bring it up by making it negative. So this would be 7x to the negative 2, and now it would be rewritten where we could apply the power rule. So let me go ahead and rewrite our integral. So I haven't, again, taken any derivatives at this point. I've only simplified using algebra. So that first fraction is going to be x to the negative 5/3, and then minus 7x to the negative 2. And the dx is still there. And now at this point, we can apply the power rule to get the integrals. So the first one would be x to the negative 5/3 plus 1 over negative 5/3 plus 1 minus 7 times x to the negative 2 plus 1 over negative 2 plus 1, and then plus c. So this is our answer. The last step would be to simplify. So let's see, I can get a common denominator. Whenever there are fractions, getting common denominators is what's going to help. So this is going to be x to the negative 2/3 over negative 2/3 minus 7 times x to the negative 1 over negative 1. I'm going to move my work here and just so I have some extra space to do the simplifying. Because there really is a lot of algebra that we're using for this particular problem. So for that first fraction, one rule from algebra 2 is that if you divide by a fraction, it's the same thing as multiplying by the reciprocal. The reciprocal just means to flip that fraction. So this is going to become negative 3 over 2 times x to the negative 2 over 3. For the next one, we've got negative 7 divided by negative 1. So that's going to become plus 7 x to the negative 1. And then I don't want to forget about the plus c. So this is simplified. And we could leave our answer like this. If we wanted to do anything else, we might go ahead and you could actually make the exponents positive by rewriting that in the denominator instead. But I'd say either way would be correct and simplified. But let me go ahead and just show you what I mean. Is that you could rewrite this as -3 to x to the positive 2/3 plus 7 over x to the positive 1, which I can just write as x, and then plus c. So that's also another way that you can write the answer for this one. Now for the last example for this section, let's look at one application. Under certain conditions, the number of cancer cells N of t at time t increases at a rate of N prime t is equal to 50 e to the 0.3219 t, where 50 is the rate of increase at time 0. Find a formula for the number of cells after t days, given that 300 cells are present at t is equal to 0. So there's sort of a lot to figure out here, but let's kind of break it down. So first, I just want to note that we are given a function, an equation, but the equation that we're given is for the derivative. And remember, a derivative tells us how things are changing. And that's why it's saying that they're increasing at a rate of this. So this is telling us the rate at which the cells are increasing. So that's another indication that we're talking about a derivative. We want to find the formula for the number of cells. So not how the cells are changing, not the rate of increase for the cells, but the actual number of cells. So that means we're going to work backwards to find just N of t, which is to integrate. So let me go ahead and write this as an integral. So N of t is going to be equal to the integral of the derivative. So that means N of t is equal to the integral of 50 e 0.3219 t dt. So let's start by just finding that integral. So we're going to use the exponential function rule, which means it's going to be e to the 0.3219 t divided by basically the derivative of that exponent. 0.3219. And now what we've talked about with integrals already is that idea of plus c. So I'm going to simplify it a little bit because I'm just going to plug into the calculator the 50 divided by that decimal in the denominator. And so that gives me that if I just want the number of cells, I can use the function 155.328. I'll round it to 3 decimal places here. But I'll actually keep it stored in my calculator to get to keep all the decimals. And then e to the 0.3219 t, but then there is this plus c. Okay, so how do we figure out this value c, this unknown constant? This extra piece of information is basically saying that we can plug in t is equal to 0 and use that to find the value c. And so because we have, when we take integrals, this extra value c, then we do need a little bit more information in order to be able to solve for it. So what we're going to do here, I'm going to say, so 300 cells, so that means the N of t is 300. I'll leave the rest of it there. And then now for t, I'm going to plug in 0. And now let's go ahead and solve this equation. So for the e, we have the 0.3219 times 0, which is just 0. And so we get e to the 0, which is just 1. So the last step is to subtract that from both sides. And so we get about 144.67. So to put it all together, the final answer is going to be 155.328e. Let's see if I can fit it all on here. 0.3219 t plus 144.67.